Hi everyone, so this is our first flipped lesson and it won't be the last one. And most of what we're going to learn today, as you can see, is things that you already know from the IGCSE. So the theory is going to be very, very easy. That's why we're flipping it. There's very little theory in the IB course, and what's hard are the problems. That's why I think it's worth it for you to learn the theory at home and then come to class and try the problems, which is what's really, really tough. And that's where you really need my help, and you need to try and you need to get a lot of practice. So anyway, this is what we're going to learn today, or to review today: the concept of displacements, distance, speed, velocity. And then we're going to do something new that you didn't do in the GCSE, which is the concept of reference frame and relative velocity. It's not that complicated, but it is very interesting, and it sets the stage for much harder stuff that we will do at the end of the course. Now, we're going to be dealing always with one-dimensional motion, at least while we're in SL. When we go to a higher level, then things will change and we will be dealing with two-dimensional motion, and all these concepts of vectors and things like that will become very important. But for the moment, we will restrict ourselves to one line. And what we do is we need to mathematically treat this line. So we say, well, okay, this is a line, this looks like the real line, right? The line of real numbers. But I don't know where the zero is, so I just choose one arbitrary point, call it point O for origin. So this will be my origin. And then I need to define some concepts on it, right? So for example, here's my car that's at the origin, and my car moves over here. And then I can make some divisions here and decide that this is 1 meter, for example. And I say, well, my car has moved 1, 2, 3, 4 meters. All right. And then what I say is that my car has moved a distance of 4 meters, because that's the difference between here and here. Of course, I could also move my car here, right? So 1, 2, 3, 4. And if I move my car here, I would also say that my car has moved 4 meters from the origin. And that's a little confusing, because we see that the concept of distance is not very precise. Yeah, okay, I've moved 4 meters, but where? Right? And if we were in 2D, for example, the car could actually move over here or over here. That would still be 4 meters, and that wouldn't tell me anything. So we need two concepts here. Right? The first one is just distance, which is what everybody understands by distance, which is just how many meters are there between point O and the point where I moved. But then we think, okay, so how can we do it so that this thing is not the same as this thing? And that's why we introduce the concept of displacement. And what we say is, well, look, here you went from 0 to 4, so 4 minus 0, that's 4. But here you went from 0 to minus 4. So minus 4 minus 0, that's minus 4. So here you really moved minus 4 meters. Oops, sorry. Here you really moved minus 4 meters because you went backwards, whereas here you moved plus 4 meters because you went forward. Or alternatively, you could say, okay, to the right that's positive, to the left that's negative. And that's what displacement is. Displacement tells us the difference between the last point we reached and the first point we were at, and it can be both positive and negative. And whether it's positive or negative is going to tell us whether we're moving to the right or to the left. So let me just write that down. Displacement. And you may be wondering, well, but why do we have to do it like this? Why can't this be 4 meters and this be minus 4 meters? And the answer is that, yes, this could perfectly be 4 meters and this could perfectly be minus 4 meters. It's completely arbitrary. And as long as you keep consistent in your signs, it really doesn't matter at all what you choose. However, we normally choose the left to be negative and the right to be positive simply by convention. Similarly, we choose up to be positive and down to be negative. But you could do it the other way around, and as long as you keep things consistent, everything is going to work out. Now, we're not in the IGCSE anymore, and we will have to do a lot of math, and we're going to need really long formulas. So we can't be writing things down like this anymore. We can't say velocity equals distance times time. We're going to go nuts. So what we need is some shortcuts to represent these two concepts. And what we're going to do is we're going to use two different letters. Now for distance, we're going to use the letter S. And you'll say, well, that makes no sense because there's a D at the beginning. And my answer is, yes, you're right, but we're just a little weird in physics. And S stands for spatium, which means space in Latin. Well, people are weird. So distance, we represent it with the letter S. Now displacement, we're going to represent it with the letter X. Now, when we're talking about displacement in 2 dimensions, or 3 dimensions, or even 4 dimensions, we're going to use the letter R instead, with a little arrow on top, because it's a vector. But for the moment, we're just going to restrict ourselves to distance, S, displacement, X. If we want to talk about movement, we need to use the concept of time, right? So this car is here at the origin and starts moving this way, and it takes a certain time. So once we start talking about time, we can start talking about speed, velocity, and all those things that you learned in the IGCSE. And we can do this a little better than we did in the IGCSE. Now, the first thing that we will talk about is, of course, speed, because that's the one you're familiar with, right? So imagine that this guy moves a distance of 5 meters in 1 second. Well, then it's moving at a speed of 5 meters per second, because the speed just tells me how many meters I move every second, or how much distance I do every unit of time. So my unit of time could be hours or years, but in this case, my unit of time is a second, right? So if I move 5 meters in 1 second, 5 meters in 1 second, then I know that my speed, which I'm going to write as v, is going to be my distance, s, over the time it took me, t. However, this is not very precise, because that's not really my speed. That's my average speed. And what I mean is that this car maybe took 1 second, but maybe was really slow at the beginning and then did this, or maybe was really fast and then did this, or maybe did this, but it just took him 1 second, right? So in order to indicate that this is not my speed but my average speed, I'm going to write a little bar on top. So this says that my average speed is just the distance that I go through divided by the time that it took me to go through that distance. Now this is all well and good, but this is not perfect at all, right? So because if I'm in my car tells me its speed, but it doesn't tell me its average speed. What it tells me is its speed at each moment. Okay, and that's not the average speed. That's the speed, or some people call it the instantaneous speed. It's the same thing as speed. So how can I find out the speed of a car at each instant? And the answer is really simple, really. It's just, well, all I need to do is to take a very, 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 very tiny instant of time, and then if I divide the tiny distance that I went through over the tiny time that I spent, then I'm going to get the speed precisely at that time. And that's actually how your car measures its speed. Now, in order to represent this, I'm going to say, okay, so speed, and now there's no little bar on top, because this is just speed, is going to be equal to a very small increment in my distance, and I will represent this by this weird letter here. And that just means a very small increment in my distance. So a very small increment in my distance over a very small increment in my time. And that's how we actually define speed. When you learn calculus, you will see that this corresponds to something called the derivative of the distance. And it will simplify things a lot. Unfortunately, you don't know calculus yet, so all we're going to say is that my speed is just a tiny increase in my distance over a tiny increase in my time. Okay, now it's time to talk a little bit about notation, just for a moment. So imagine that here's my car, but my car is not here at the beginning. My car is here at the beginning, and then it moves under here. Now, I'm not really interested in the displacement now, because, okay, my displacement at the beginning was 5 meters, and now it's 8 meters. But what's really interesting to me is not where it was at the beginning, but how much it moved. And it actually moved 3 meters. So what I'm interested in is the increase in my displacement. Now, we could write down increase in x, But again, when we have to write these 30 times in the formula, we're going to go nuts. So instead of this, we're going to use a little tiny shortcut. And instead of increase in, we're going to write this little symbol. So whenever you see this symbol here, this means increase in whatever comes here. Okay? So in this case, if I write delta x, and this thing is called delta, this means increase in displacement. So this will stand for the increase in displacement. And this is a quantity that I'm going to need in order to define velocity. And the idea of velocity is that I'm at a certain point, and then I move to another point, and there has been a certain increase or even decrease, which is also represented by the same letter, because a decrease is just a negative increase, of my displacement. So my velocity will be determined by how much my displacement increases or decreases per unit time. So how can we express this mathematically? Well, same thing, same way we did before. And I'm going to use exactly the same letter. And I know this doesn't look very precise, but most of the time we will know whether we're talking about velocity or speed. So it doesn't matter. We just write v all the time, and it's clear whether we're talking about speed or velocity. So I'm going to say that the average velocity is just the increase in my displacement divided by how long it took me to do that. So divided by the time. And bear in mind then that, for example, if I go from, let's say, 5 to 8, then the increase in my displacement is 3, and if that takes me 1 second, then my average velocity is 3 meters per second. But if I went from 5 to 2, then the increase in my displacement would be minus 3, because I moved 3 backwards. So my average velocity would be minus 3 meters per second, which means that average velocity can actually be negative. Speed cannot be negative, velocity can be negative. And the reason for that is that velocity is a vector, whereas speed is not, it's just a scalar. Now, we can write this thing a little bit more formally, and I'm going to write down here, but it's really obvious, and you should not memorize this. You should, if you understand what an increase is, then this is just common sense. So I will say that the increase in displacement is just the final displacement minus the initial displacement. And this makes sense, right? So if I'm over here at 5, that's my initial displacement, then I move to 8, so 8 minus 5, that's 3. If my initial displacement is 5 and my final displacement is 2, then I got 2 minus 5, that's minus 3. And that's it for the average velocity. But of course, we're not happy yet, because the average velocity is not very precise. Again, I could be moving from here to here at the same speed always, or I could be doing this, or I could be doing this, and whatnot. So what I need to do is to define a quantity that tells me my velocity at each instant. And pause the video and ask yourselves, how would I define this based on what I just saw that we did for speed? Pause the video, give yourself 5 seconds to think about it, then unpause. Alright, so hopefully you did what I asked you to do and figured out that then the velocity will be same thing. Tiny increase in displacement over a tiny increase in the time. And that's how we defined instantaneous or just plain velocity, whereas this is average velocity. So all this time we've been talking about velocity and speed and all that stuff, but we have never asked ourselves who is measuring this stuff. So here I've got a car that's moving this way, and then I say this car is moving at, let's say, 20 meters per second. Says who? Well, a person inside the car would completely disagree with you. A person inside the car would say, well, no, my car is still. Well, that person has a little problem because its legs and arms are at the same place. But anyway, this guy here would say, well, no, my car is still, because this guy is moving this way, and actually, no, it's not moving anywhere. Like, it's always at the same place. It's just under my feet. So its speed is 0 and its velocity is 0. And however, a guy here on the road would say, no, 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 no. You and this car are moving this way. And this guy would say, no, 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 no. You are moving this way. I'm still. And then a guy on a train here, so this is a train, believe it or not, would say, no, you guys are both wrong. You are moving this way very slowly, you're moving this way very fast, and I'm still on my train. Whereas this guy would say, no, 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 you're moving very fast this way, and he's moving this way a little more slowly, and he would say, no, 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 you're moving this way, I'm still. So as you can see, all this velocity stuff depends on who's measuring it. Now, the person who is at some point measuring stuff with a bunch of clocks and a bunch of rulers, we call that a reference frame. And for any movement, we could have a number of reference frames. So we could have a reference frame of a guy who's still on the ground. We could have a reference frame who's moving with a car. We could have a reference frame on a train. We could have plenty of reference frames. And the question is, who's right? Is this guy right? Is this guy right? Is this guy right? Well, actually, they all are right. As long as they're moving at a constant speed, the laws of physics that they see will be exactly the same and as long as they keep consistent and apply the laws of Newton consistently, they will all see things that make sense. So, and they will make exactly the same prediction. So the three reference frames are exactly as valid. A guy who's standing on the ground, a guy who's on the car, it doesn't matter, they will all see exactly the same thing. And even though their velocities will be different, what ends up happening at the end will be exactly the same. Now, a very interesting concept that's related to reference frames is the concept of relative velocity. And I'm sure you guys will be familiar with this. So imagine that there's a car here, and then there's another car here, and they're running towards each other. So, and then here there's a guy who's still on the ground. Well, according to himself, he's still on the ground. According to them, he's moving. So, according to this guy, this car is moving this way, and this car is moving this way. Let's just say he's moving at 50 kilometers per hour, and he's moving at 20 kilometers per hour. Now, so the relative velocity of this guy with respect to this guy is 50 kilometers per hour. The relative velocity of this guy with respect to this guy is 20 kilometers per hour, which is basically when we say relative velocity, we mean the velocity that this guy here measures. So now let's think about what this guy here in this car is going to measure. So here's our new guy who's driving in a transparent car. And what's the relative velocity of this guy compared to this guy? Well, it has to be minus 50 kilometers per hour because this guy is now still and this guy looks like it's moving backwards at 50 kilometers per hour. So this should be minus 50 kilometers per hour according to this guy. So that's the relative velocity of this guy according to this guy. Now this one, of course, was minus 20, not 20. So what's the relative velocity of this car according to this car? Pause the video and give me an answer. Okay, again, hopefully you did what I asked you to do. And if this guy thinks he's still, then he will see this car approaching him at 50 plus 20 kilometers per hour. So the relative velocity will be minus 70 kilometers per hour. Similarly, according to this guy is moving this way at 20 kilometers per hour. This guy is approaching him at 70 kilometers per hour. So again, each one of them will measure a different relative speed, but if we know the relative speeds, we can figure out the relative speed from the other point of view. And that's what relative speed is. The funny thing about this is that when we learn relativity, we will see that this answer is actually wrong, and that the relative speed of these two is actually less than 70 kilometers per hour. However, it's so close that for all intents and purposes on the road we can say that the relative speeds of these two are 70 kilometers per hour. And now comes what's probably your favorite part of kinematics, which is making graphs. And you may remember from last year that there were two types of graphs that we made. We made velocity time graphs and we made displacement time graphs. You can also make speed time or distance time, but normally we prefer velocity and displacement. Actually, this shouldn't be a D, this should be an X, right? Because now we're calling this X. Alright, so for a car that's moving at a constant speed, how do you think the velocity time graph is going to move? to look like. Pause the video, say an answer in your head, and see if you got it right. Well, of course, constant speed means that speed is always the same. So a velocity time graph is just going to be a straight line at the same height all the time. A very boring graph. Now, if the guy is moving backwards, how is it going to look? Well, if it's moving backwards, then the speed will be negative, so it will look something like that. How about for displacement time graph? So this same guy here, how is the displacement time graph going to look like if the guy starts at zero displacement? Well, if he starts at zero displacement, this is telling us that it goes to the same number of meters every second. So 1 meter, 2 meters, 3 meters, 4 meters, every second. So this should be a straight line going up. In this case, if we again assume he's at zero displacement at the beginning, he's going backwards always at the same rate. So this should be a straight line going down. However, this doesn't have to be like this. This line here could actually be here. Depends on the initial displacement. It depends on where this guy was at the beginning. And this line here could actually be here. So for example, the guy could already start at 10 displacement and then he just gets further and further and further away. So this graph, we don't have enough with this graph to make this one. We actually need this graph so that we know how the displacement increases, but we also need to know the initial displacement. Otherwise, we don't have enough information. Now, a really neat property of these graphs is that we can use this one to calculate things about this one. And the reason is that if we calculate the area under the velocity time graph, what we get is the increase in displacement. So this area here will give us the increase in displacement at any time. And even though here it doesn't seem to have a point to do this, because all we need to do is multiply velocity and time and we're done. When things get a little bit more complicated, this will be a godsend. It's going to be very, very, very handy to know that all we need to do if we want to know the increase in displacement is just draw ourselves a graph, calculate the area under it, and we're done. Alright, so that's the end of the first flipped lesson. I hope you understood most of it. If not, the beauty of this is that I will be there to help you when you struggle, because you will be in class working and I will have plenty of time for you individually and we can work things out together. Anyway, after this is what you should understand. You should know how to define displacement. Hopefully you know how to do that. You should know how to define distance, speed, and velocity. And again, I think that after this video, this should be no problem. And finally, you should understand what a reference frame is and what the relative velocity between two bodies is. If you know this, you're in a good position to start doing the problems. Now, don't think that because this is very easy, the problems are going to be. Physicists have a knack for taking some really easy concepts and making some extremely devious problems out of it. So don't get frustrated when you start doing the problems next day in class and you get stumped, because you will get stumped. And that's why I'm there. And that's how we learn. So practice, 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 and we will all get there eventually. Good luck.